Hello everybody. Hopefully you can hear me. We are picking up where we left yesterday, so if you had those, pull those out. We're actually going to skip number 3 real quick. We need to kind of do the next page actually before you're going to be able to do number 3, so we'll probably come back to number 3. Go on to number 4 real fast. And kind of a quick little review of what we were doing yesterday. You have at the top of your paper there is just these ideas of how we can determine if something converges or diverges. Here was what you had quizzed on. It needs to pass the nth term test. That's pretty much number 1 and 2 in saying. And then if you can determine that it's a geometric series, then as long as your ratio's absolute value is less than 1, we're good. Harmonic series passes the nth term test, but doesn't converge as a series, so that causes the problems. That's why we need these other tests. Yesterday we did the comparison test, and that's kind of where we're leading off at this point. And what the comparison test then said, you kind of have right here, is that as long as the series we are concerned about is less than a convergent series, then our series would converge. And then this is saying as long as our series is greater than or equal to a divergent series, then our series then would have to diverge as well. So that's kind of what we were working on. So number 4, if you kind of go to that one, would be if we are comparing, if we were going to be doing this here, all of our old tests still kind of pop up in terms of how we would be able to do a question like this. So the first thing we are always doing whenever we're doing one of these problems is making sure that it passes the nth term test. If it does not pass the nth term test, then we know it's going to diverge. So that is still your first step. So in number 4, the first thing we're going to do is determine as n goes to infinity, will this sequence, so if we kind of ignore the idea that we're adding everything together, will this general term go to 0? So basically what that's asking is if we were to compare a root n and a natural log of n, what we'd hopefully know from the other day is that the natural log of n is Ahmed, and he doesn't beat anybody, okay, because he's slow. So that root n, even though root n grows pretty slowly, it does grow faster than Ahmed. So since this is faster, all right, this fails the nth term test. So we would say that this limit is infinity, and therefore this would diverge. You would say the nth term test, the limit as n approaches infinity for our general term is infinity, which then obviously is not a 0. So the nth term test still works as long as it diverges. All right, if our limit is infinity, then for sure our limit or our series is going to diverge. You're done. You can kind of go on to the next problem. Okay. Next page. A couple more tests, a couple more ways that we can do these. The first one is called a p-series. A p-series is a variation of the harmonic series. This is pretty much what a p-series has to look like. Your numerator doesn't have to necessarily be a 1. It basically needs to be a constant, but in the simplest version, it's going to be a 1. And then you're going to have your n raised to a power. This is called a p-series in this form. If you kind of look at what I have there on the paper, if p equals a 1, think about what that would be. It's 1 over n to the first. You have the harmonic series. So in a p-series, if your p is a 1, you're basically dealing with the harmonic series, which we already know would diverge. If p, if you kind of look at number 2, is greater than 1, so if we have a constant and then n over a certain value, then your series is going to converge. If p is less than 1, then your series is going to diverge. Okay? So that's kind of what the p-series is saying. So as long as p is greater than a 1, you converge. As long as you're less than 1, you're going to diverge. Okay? All right. Second thing, an integral test. What the integrals test is saying, if you have a series, so our nth term, this a sub n, if we let that be a sequence of positive numbers, what the integral test is basically telling you to do is take the general function here and rewrite it as like a regular function. It's like a function we're used to. If it's continuous, positive, decreasing, all that good stuff. But what this ultimately says is, if we want to know if this series would converge, what we would basically do is an old idea. An idea that we did not like particularly well when we did it. And that is by setting up an improper integral. An improper integral is one of the ones where we let our upper limit be infinity, or one of our limits is undefined. If we can evaluate this integral and this integral converges, then that would mean our series would converge. If we set up an integral with this and the series diverges, then that means our series would diverge. Okay? So to show that, we're going to kind of prove the P series at the same time. So number one, we're going to do this one. We kind of already know the answer to that. So the harmonic is going to diverge, but we're going to show the integral tests, or use the integral test to show that. Here, based upon the P series above, that is a P series and is greater than 1. Therefore, this will converge. This should actually, now that I look at it, say, show that that series converges. So you may want to add that in now that I look at it. 7, we'll do this one as an integral, and then actually we're going to add one too in a second, but we're going to basically do the integral test for these. So number 5, what this is saying is if you have an infinite sum, starting at 1, going through infinity, what the integral test is saying is we're basically going to rewrite this as an integral from 1 to infinity. And we're going to integrate this. All right, do the integral test. If you remember when we did these are the ones where we would then say let your infinity limit, the limit that's a problem, be your b. So we're going to do that. Once we do that, we can finish this off. This obviously is a natural log, absolute value of n from 1 to b. You'd plug in your upper limit, subtract your lower limit. At this step here, you're kind of done. This obviously is going to be a 0. So what we need to know is as your b, if you remember when we did these, we now calculated the limit as b approaches infinity, since that's what the b was substituted for. As b goes to infinity, we always then ask what happened to the natural log curve. So this is when we had to kind of understand the graph. The natural log curve looks like this. And as we go further and further along the x-axis here, even though it does it very slowly, the natural log curve does increase forever. So this thing goes to infinity. That then, when we did these, would mean this diverges. And that's ultimately what we wanted to do, is use the integral test to show that this does in fact diverge, and that's what we just concluded here. 6, similar. This should converge based upon the P series up at the top of the page. We're going to show that using an integral test. So we're going to rewrite this guy here, the infinite sum, as an integral from 1 to infinity. And then we're integrating 1 over n squared. I'm just going to rewrite that real quick. We're going to have to do that at some point. So bump your n squared up so it's n to a negative 2. We'll make the antiderivative easier. We're going to say that this is b. All right, b is your infinity. So do our antiderivative. That's going to give you an n to a negative 1 divided by a negative 1 from 1 to b. Simplify this. All right. As you can see, the annoying cat is on the table. Get out of here. Sorry about that. All right. Let's see here. All right, rewrite this guy as a negative 1. That's my wife's cat, by the way, not mine. From 1 to b. So we just rewrote this, negative 1 over n. Plug in your upper limit, so negative 1 over b, minus a negative, plug in your lower limit, 1 over 1. So this ultimately ends up being a plus 1. This should converge, all right, based upon the P series that we talked about at the top of the page up here. So you're going to see that this now will converge, because now as we calculate our limit, as the b approaches the infinity, this here goes to 0. Which means you end up with a 0 plus a 1. This converges to 1. Okay, so that converges. I don't have it. We're going to do it. Add it at the bottom of the page. Did I start with number 9? Yeah. Go to the bottom of this page and label this. We'll call this 8b. And where you're going to put it in an 8b is our infinite sum. We're going to let this be 1 over n to the 1/2. All right, so hopefully that looks like a 1/2. What we're going to do is show that if your p is less than 1, all right, this guy here, then we should diverge. So that's what we're about to do here. So it's one more using the integral test that you're going to do. So you're going to go from 1 to b. This is n to a -1/2. Do your antiderivative, so you're going to get n to a +1/2. We would divide by half, which is multiplying by 2 from 1 to b. Plug in your upper limit, so that's a root b minus a root 1. Calculate your limit now as your b goes to infinity. And then as your b gets bigger and bigger and bigger and bigger and bigger, the square root curve gets larger and larger and larger as well. Therefore, this does in fact, like it should, this diverges. Okay? So that's just using the integral test, kind of proving the p-series. If you ever have p-series, you don't really have to do that. You can just tell me that it diverges because of the p-series. Okay? This one here, the way we would do this, set up another one from 1 to b. We're going to have to integrate this thing, 6n squared n cubed plus a 1. This is going to have to be a u substitution problem. You're going to let u be n cubed plus a 1. du is 3n squared dn. We need it to be a 6, so we'll just double each side here. Substitutions are all set. Your integral would now have u in your denominator, 6n squared dn. Yeah, there should be a squared here. Alright, the 6n squared dn, so 6n squared dn, we can get rid of that with a 2 du. Get your new limits using this. So our lower limit was a 1, you plug that in, it's now a 2. Our upper limit was a b, plug that in, that is now a b cubed plus a 1. So do your antiderivative. I'm running into this, so let's take this over here. 2 natural log u from 2 to the b cubed plus a 1. See, you can probably hear him, he's annoying. Plug in your upper limit minus your lower limit. And then now we just see what goes on as your b goes to infinity. So should be able to do that as b goes to infinity. So as your b gets bigger and bigger and bigger and bigger and bigger, so this would get larger and larger inside. So then that now asks the question, what does the natural log curve do as we get further and further and further to the right? That overall goes to infinity. Therefore, this would also diverge. Okay. All right. Let's see here. The last one. All right. E to a negative n. Write that as an integral. 1 to b. E to a negative n. dn. Does this converge? We would basically do this with the integral test, doing your antiderivative right away. Should be e to a negative n. You would divide by that negative 1 from 1 to b. Simplify that real quick. 1 over e to the n from 1 to b. So we would get a negative 1 over e to the b minus a negative 1 over e to the 1. End up adding those, and then now we just calculate the limit as our b's get larger and larger and larger and larger. This guy definitely goes to 0. You end up with 1 plus 1 over e. So this does in fact converge to a sum of 1 over e. Okay? That's the integral test. All right, next page. This is where these get a little dicey because it now says determine if the following series converge or diverge. If the series diverges, state the reason. These are all just mixed up. So any test that you've done so far, you can use here. But again, always, 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 your first test always is the nth term test. All right, see, nth term test. All right, Determine if the following series converge or diverge. We first want to make sure this would pass the end term test. So that is simply saying, oh, it's really out of focus. All right, as n goes to infinity, so I guess we're just doing this one, would that sequence, so if I got rid of the series here, would this sequence go to 0? Okay, definitely does, passes the nth term test. All right, but like the harmonic series showed us, just because it passed the nth term test doesn't necessarily mean that it's going to converge. So that's why we need other tests. All right, this is one of the first ones we've done. You see a 10 being raised to an nth power. That tells us this is geometric. If you needed to, hopefully we would get to a point, if we're not there yet, where we would just know this is 1 over 10, 1 over 10 squared, 1 over 10 cubed, so on and so forth. We would be able to look at that, know that our ratio is 1/10. All right, that's what we're multiplying each preceding term by to get the next term. So in terms of determining if this converges or not, we should be able to look at that, know that it's geometric. We would know that it converges because it is a geometric series. With the absolute value of our ratio equal to a 1/10, which is less than 1. I don't really need you to find the sum right now. It's not what we're looking to do. We could if you wanted to with our little formula, but right now we're just saying does this converge or not, and if it does or does not, saying why. So that's pretty much it for number 9. All right, B, letter B, again, you're going to do that first, all right, nth term test. So when we do that, as your n goes to infinity, when we look at this, we should be able to conclude that that actually has a limit of 1. The only way that it passes the nth term test is if this would have been a 0, but since we have same degrees, coefficients 1 over 1, that means this diverges. Nth term test. And then you would say limit as n goes to infinity for our nth term is a 1, which is not 0. 11, 2 to the n over 3 to the n. Again, hopefully, well, let's first check nth term test here. So if we did as n goes to infinity, all right, this needs to go to 0. Hopefully we would know this does in fact go to 0. You're basically, when you're dealing with these, figuring out which one of those grows at a faster rate. So we did a few days ago. Since the 3 to the n has a bigger base than this exponential function, which has a base of 2, this does in fact go to 0. All right, this is a faster growing function. So as n goes to infinity, this would go to 0, meaning it passes the nth term test. So now the question is, does it converge? The nth term test is not enough to determine that. Should be able to look at this. Note this is 2 to the n, this is 3 to the n. So that basically means our first term is 2/3 plus 2 squared over 3 squared, 2 cubed over 3 cubed. This is a geometric series. We're multiplying the numerator by 2 each time, your denominator by 3 each time. So your common ratio here, if we were to continue on, is a 1/3. That's good for a geometric series to converge. So we could then say that this does converge. It's a geometric series. With the absolute value of our ratio equal to a 1/3, which is again less than a 1. Okay. All right, 12. If you look at 12, definitely passes the nth term test. As n goes to infinity, this is a constant in your numerator. Your denominator does grow to infinity. So over time, this will go to 0, so it passes the nth term test. So then we have to kind of explore the other options in terms of figuring out what you're going to be doing. When we look at that, we should definitely see that is not a geometric series. We're not going to be able to rely on that You don't have an exponential function, a constant raised to a variable, so can't do a geometric series. So your other options are a comparison test and the integral test, or a p-series. Definitely not a p-series. A p-series has to be just like a 1 over n to the 4th, or n squared, n cubed. You have that here, but with the natural log in there, definitely not a p-series. Leaves us pretty much either to integrate that or to compare that. I kind of want to do a comparison test just to sort of show you what happens sometimes with these. What we want to do when we compare is, again, keep your numerator the same, or one or the other. Keep one or the other the same, usually the constant and what's going to stay the same. And we just want to tweak the other one. So if we're going to keep our numerator the same, we just want to tweak our denominator. And the way we can do that is to just get rid of the ln of n and rewrite that function as 1 over n. The reason this is a good function to compare it to, because you know this series diverges. So if we can show that this series is greater than this series, then we would know that our series diverges. Okay? So that's our hope. The problem with that is, since your numerators are the same, this denominator is always going to be bigger than this denominator. So the fact that the numerators are the same, and this one's always going to be getting divided by a bigger number than this one, means that each term in the left one is going to be smaller than the one on the right. This is inconclusive. If we are smaller than a divergent series, it tells us nothing. This could diverge, it could just diverge at a slower rate than this one. So comparison test, unfortunately, no good. What that leaves us with is one and only one option, and that is to integrate this. So that's what our plan is. We're going to integrate this thing. You're going to go from 1 to b, and then 1 over n ln of n. You'd have to do u substitution, let u be an ln of n. du is 1 over n dn. Substitute, get your new integral. You now just have 1 over u du. Get your new limits using this. So you take your 1, plug it in, you'll get 0. Take b, plug it in, you'll get the natural log of b. Alright, pretty simple. That's our natural log. From now 0... time out. Let's not make this too hard. Go up to this, make this a 2. So, oops. That means this lower limit was a 2. And then that makes your lower limit now the natural log of 2. So sorry, get that corrected. Whoa, there's my ceiling. That's the natural log of 2 now, that's your lower limit, and then the natural log of b. Alright, then we'll continue on from there. So plug in your lower limit, or upper limit, sorry, minus the lower limit plugged in. And then now at this step you have to determine, as b approaches infinity, because that was our b, as the b gets bigger and bigger and bigger, this natural log of infinity grows to infinity, so the inside is getting bigger and bigger and bigger. Then we want the natural log curve. What does it do as we go to infinity? This then overall grows unbounded, which means this guy diverges. You would just say integral test. And as long as you have the work, we don't really need to elaborate on that. So if you have the work with the integral test, that's pretty much the only reasoning that you need to put down on the paper. Okay, 13. First, make sure it passes the n-term test. Not quite as obvious with this one. As n goes to infinity, the inside here, if you think about your rules of infinity, the inside of that should go to 1/3. And as the inside behaves more and more like a 1/3, it would be getting raised to an n power. So over time, it's going to look like 1/3 times 1/3 times 1/3 times 1/3, which means this does pass the n-term test. It's going to be getting smaller, 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 smaller. So pass the nth term test, that means we need to continue on. When we start exploring options for this, you're not going to be able to integrate that. Okay, good luck integrating this function raised to the nth power. This is definitely not a p-series where you just have a constant over like a 3 or an n to the third, n to the fourth, so on and so forth. It's not geometric, all right? You don't have any constant raised to a variable. So pretty much the only other option we are left with is to somehow compare this to something. What we're going to compare this to, again, what we want to do when we compare is to keep either the numerator or your denominator the same, and then slightly tweak the other one. So what we're going to do in this problem is we're going to keep the n the same, we're going to keep 3n the same, we're just going to drop out this positive 1. So what we're going to compare it to over here, the n stays the same on top. We're going to drop out that positive 1, make that a 3n, and then we're still raised to the nth power. So now, kind of think about what this is saying. Your numerators are the same, n and n. Your denominators are very, very similar. It's just that your denominator on the left is always a little bit bigger than the one on the right. So, if your numerators are the same, and they are, they're both n, and they're being divided by something similar, but this one's always being divided by a number that's a little bit bigger than that one, what that would do is show us that this guy here is in fact smaller than this one. Now, the way this looks doesn't do you a whole lot of good because we don't really know what this is in terms of does this thing converge or diverge, but what that now simplifies to be, what this really is, the ends would cancel. These are equivalent expressions. So what we have basically now just shown is that the series we were concerned about, this guy, is less than this series here, because these two were equivalent to each other. And then we know that this is a convergent geometric series. So we've just shown that our series is less than a convergent geometric series. Because of that, by the comparison test, this would converge, and that's what we then put down. So you're going to put this converges. Okay, losing focus there. There. You would say comparison test. It is less than geometric series with the absolute value of our ratio equal to 1/3, which is less, that's a third, less than 1. Alright? Alright, 14. Do 14 real quick. That should be really quick and easy. The reason that should be real quick and easy is because this guy should right away diverge. The reason it would diverge is because if you look at this, when you do your nth term test, again, which you are always doing first, as n goes to infinity, this guy grows faster than this one. The limit of the general term here was infinity. So this diverges by way of the nth term test. The limit as n goes to infinity for the general term was infinity, which then is obviously not 0. Alright, last but not least, oh no, not last, this guy. The root n over the natural log of n. Again, should be a pretty quick one. We actually have already done that, I believe, on the front page. Yeah, we already did this one. This should diverge. If you need to know why, you can go back to number 4 on the front page. Alright, same exact problem. So, no need to do that. That'll put you out of your misery a little faster with this. That diverges, look at number 15. Alright, now last but not least, state the limit to which the following series converges. The only way we can actually state what our series converges to is if it's a geometric series. Then we can use our little formula, the first term over 1 minus your ratio. That is not geometric. The only other way that we now know how to do is by integrating that, and then whatever that limit is, what do we approach, that's going to be your the sum. That's going to be what we converge towards. So basically the only way we're going to be able to do this, since it's not geometric, is by integrating it. I think you're going to like this a lot. Write that as an integral from 2 to b n squared e to a negative n. So we're going to write that as an integral, and then we're going to integrate this. All right. If I was there, I would wait until somebody told me how to integrate this. But if I did that now, there'd be this awkward silence, so I won't do that. The way you have to integrate this is a product. The only two ways we know how to do a product is by u substitution. All right, good luck doing u substitution with that. The other way that we did products is with the integration by parts, the whole uv minus the integration of v du, okay, that stuff. Or the alternative to that was your tabular method. So that's our route. We're going to use tabular integration to integrate that. So I'll set up our little table over here. We want the derivative of this, so that's our first term, n squared, then you'll get 2n to 0. We want the antiderivatives then of e to a negative n. If you remember, our general rule was we want the derivatives of the one whose derivative would eventually go away. N squared's derivative will eventually come to 0. This won't. So we need the antiderivatives of this. E to a negative n would be in the b, e to a negative n divided by a negative 1. So I'll just put that in front. Another antiderivative is e to a negative n divided by another negative 1, which now makes this a positive 1. And then our last one, e to a negative n. Ooh, it's not good. Sorry. E to a negative n divided by a negative 1. Our signs are always positive, negative, positive, negative. So when we go to do the antiderivative of this, our first term should be these two guys multiplied together. A negative 1 n squared e to negative n, you would keep that sign. So you get a negative n squared e to a negative n. The next term would be these two multiplied together, so 2 times 1 is 2, but we want the opposite of that, so that should be a negative 2 e to negative n. Last term, these guys multiplied together would be a negative 2 e to a negative n. From now 2 through b. All right. Next step, you don't necessarily have to do this, it would work, but I'm going to pull out a common factor of negative, 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 and they each have a e to a negative n. So we're going to pull out a negative e to a negative n. That would now leave us with an n squared plus, this should be a 2n here, plus 2n minus 2. Or sorry, plus 2, because we're changing all those. From 2 to b. All right. Go ahead, plug in your upper limit. So you're going, actually, let's do it this way. Let's do, let's see here, our n squared plus 2n plus 2. Leave these parentheses here, put the negative out in front, and then we're going to put this e to a negative n in our denominator. It's probably the safest route to go. So we still have this 2 to b, and then plug in your upper and your lower. So you're going to get a negative, plug in the upper limit, b squared plus 2b plus 2 all over e to the n. Minus the negative, and then you plug in 2 in for all of those. So you're going to get 4 plus 4 plus 2, all divided by e to the n. And then we can add these. Oh, sorry. losing focus here. When we plugged in our b, you should have b squared 2b. This is also a b. Same thing should have happened here. Plug in your 2, you get 4, 4, 2, e to the 2. So that's an e to the 2. Alright, done it a bunch of times today. See what happens now as b goes to infinity. Alright, that's what we're left to do. We need to figure out in this part of it here, as b goes to infinity, what's going to happen here. This goes to all of our tests. If we were to raise a regular old polynomial function with an exponential function, we would know that the exponential function grows faster. Because the exponential function grows faster, this whole thing then would have a limit of 0. Since that's a 0, you end up with 0 plus 10 over e squared. Alright, that's what we would be converging to. Okay, that pretty much wraps it up. We will be a day behind, so whatever we had planned for the next day, we'll do that on Monday now. So that's a wrap. Have a good break. We will see everybody on Monday. Don't do anything I wouldn't do this weekend, and we'll see you then. All right, bye.